This is lecture 27, Monte Carlo simulation applications. And today's applications will be on a radiation shield and on an explosives detection system. Okay, so let's begin with the radiation shield. And this shows you what I'll be talking about. So here is radiation coming from the left side. Here's a person standing, and here's a shield in between. And so what I'd like to do is I'd like to stop this radiation so that less of it comes out, and what comes out is within the safety limit, within the acceptable safety limit. So this is the MCNP file, again, 3 blocks, 1, 2, and 3. So let's see, in the first block, I have the title card, that is slab, shield, and I did the simulation on 8th of May 2020, and these are the cell cards. Now again, I've got, like Godiva, I had a sphere, now I've got a cube. A cube has 6 surfaces, so I need to have 6 surfaces over here, 1, 2, 3, 4, 5, 6. Now the first 2 surfaces are normal to the x-axis, so that x equal to 0 and x equal to 20 centimeters. Surface number 20 and 30 are normal to the y-axis, -5 centimeter and +5 centimeter, which means that they're of thickness 10 centimeters on the y-axis. On the z-axis, again, surfaces 40 and 50 have a thickness of 10 centimeters between minus. So let's say that this is the x-axis, and that's the y-axis, and that's the z-axis. So this distance is 10 centimeters, this distance is 10 centimeters, and this distance is 20 centimeters. So the first, the shield itself is cell 1, and it has material 3. I'll just take you down to material 3. Material 3 has a density of 1 gram per cubic centimeter, which means it is water, and it is to the right of surface 1, which is this, left of surface 2, which is this. So it's between these two in x. It is greater than 20 and less than 30 in the y direction. It is greater than 40 and less than 50 in the z direction. The outside world is cell number 12 with nothing in it, with a void in it. So I'm not interested in air, I'm going to call it void. Of course, in real life, you'd have air and humidity, so you need to model it with real life conditions. For the time being, let me just say that there's nothing outside. Again, this is a non-re-entrant surface, which means that once radiation is left, it's not going to come back over here. Okay, so this is the outside world. The outside world is opposite of this. So if this was greater than 1, this is less than 1. That was less than 2, this is greater than 2. So all the signs over here are inverted over here. So it's the outside world. And there is a union, there's a union operator. So when you don't have any Boolean operator here, that means the intersection. So this is the intersection of everything to the positive of surface 1 with that of negative to surface 2. So this is the union of everything less than surface 1, everything greater than surface 2, everything above this, everything below this, everything in front of this, and everything behind it. So that's what we call the outside world. Now the surface cards also I took you. Let's look at the geometry. Now we just have one material, which is material 3, which is water with a gram density of 1 gram per cubic centimeter. Okay, now let's look at the third. So these geometry cards were supposed to be, this label was supposed to be in block 2. But it's a comment card, so it doesn't make any mistake to my simulation. Okay, so it's a neutron photon problem. Why? Because I've got a neutron source, but those neutrons can generate photons, and I don't want to kill the photon when it's generated. So I want to do combined neutron and photon transport. Now MCNP can also do an NPE, neutron, photon, and electron problem. But right now, let's just do a neutron photon problem. The two importances I set for neutrons, 1 inside the shield and 0 outside. So 1, 0, 1, 0 for photons, 1, 0 for neutrons. Okay, now this is the material 3 that I'm going to use. Material 3 is H2O. Again, I'm not specifying the cross-section library because I'm letting MCNP select its own default value for the hydrogen cross-sections and for the oxygen cross-section. Okay, now let me define my source. I say that the position is X, Y, Z. Why don't I take X equal to 0? I can do that, but I just want to take it slightly to the right of the boundary. I don't want it to coincide with the boundary. I cannot take the source in a region of 0 importance. So I cannot do that. So this is the position of the source, and the energy of the source is 1 MeV. The particle is a neutron, and this is the anisotropic source along the unit vector along the x-axis. So the direction of the source is here, it's in the vector 1, 0, 0. Okay, now here's the neutron current that I'm looking at, the neutron current crossing the right boundary of the slab, which is surface 2. The flux I'm going to take inside the shield. Now here, in the last problem, I did not have energy bins. So here I've got an energy boundary of the first result that I'm going to show you will be between 0 and 5 eV. And the second I'm going to show you is between 5 eV and 14 MeV. Now, the source I've got is 1 MeV. So this I've taken as 5 eV because all the thermal neutrons and the 1 eV neutrons would also be in here. So I'll just get a picture of it. So these are the two neutron tallies, the F1 and F4. Then I've got, there's also an F2 neutron tally, F2 neutron surface 2. Then for the photons, I've got a tally type 1. Since I've used 1, so I'm going to call it F11 for a photon, surface 2. So at surface 2, I'm getting the neutron current and the photon current. Now, in the cell flux, I've got the neutron cell flux in 1. I've got the, okay, I've got the surface flux of photons on surface 2. For neutrons, I've got the cell flux. Why? Because inside the cell, I would also like to estimate a reaction rate. So I need the track length estimator of the flux. Inside the cell, I'm going to multiply it by the N gamma cross section. So that will give me the number of gammas produced by the neutrons. Okay, now here are, because I've used tally number 2 for neutrons and tally number 12 for photons, so I've got to give my dose energy bin values and the flux to dose conversion factors over here. Now these I've taken from the standard ICRP, and the bin values are from 2.5, 0.025 electron volts all the way up to 20 MeV. And at those values, these are the flux to dose conversion factors. Now this is for tally number 2. Tally number 2 is neutrons. So what MCNP will do is that it will take the flux and it will multiply by the N gamma cross sections. Okay. Now, same thing for photons over here. This is called the H star 10 millimeter values. So, okay. So that's the neutron and that's the photon flux to dose values. Okay, so that's why I took the neutron and the photon flux to dose factors. Okay, now here are the reaction rates. So let's look at 14 first. 14 has 4 cards. The comment for 14 is that I'm going to calculate the N gamma reactions. And this is all, again, for one source neutron, right? This is exactly what I told you for the Godiva case, that you have got to normalize your results to the actual source that you've got. Now here, you can use a Californium source or whatever, but you have to normalize your results, but I'm going to do it for one source neutron. We can also have the multiplication factor inside over here. We can multiply in FM14, but I'm not doing that over here. So what I'm doing is I'm giving it a -1, which means that from the problem specified, get the atomic density of hydrogen. And for material number 90, which I have defined separately over here, because this is 100% hydrogen. Previously, I defined material number 3, which was not 100% hydrogen, but which was H2O. So I don't want to do it in that. So I define a material number 90, and the cross section is 1001 for hydrogen, 0.66C is the library, and it's 100% hydrogen. So the reaction number is 102. 102 means the N gamma microscopic cross section. Here's the $sign, which means that -1 multiplies the number by the atomic density of material 90 in cell number 1. So the answer that I'm going to get from here is reactions per cubic centimeter per source neutron. So that is what tally 14 is. Now tally 24 is the same thing, but I don't have a -1, I've got a +1. Okay, so here what you need to do is, now this happens in the early stage. I put it purposely for you, that first you do it with -1, then you do it with +1, and see the difference in results and satisfy yourself that here it does multiply by the atomic density and here it does not multiply by the atomic density. So 14 and 24 are tallies for H and G. Now let's look at Ng in water. Now this also I've done so that you can see that if you define another material called 92 as water, then because there's going to be some N gamma in oxygen, although much less than water. Okay, now so I'm going to take 100,000 histories over here. So the number of particles sampled is 100,000. Right now, I don't know how much computer time it will take, but I don't think it should take more than 10, 15, 20 minutes. So I've just put 100,000. If you want to specify that you don't want to do a run beyond 10 minutes, you can say instead of NPS, you can say CTME, cut me after 5 minutes or 10 minutes. Now this is a physics card for photons that you don't want to waste too much time on very low energy photons. So you can see that this is the cutoff lower point for photons, and this is the print card. So you can print your results. Now on the results of the radiation shield, I spoke to you in, I think it was lecture 23 or 22. So please see the results of it. Okay, now let's come to the second problem that I want to take you through. And this is a fixed source system again. It's an explosives detection system. And it's an interesting problem because it is identification of materials. Now, if you are working in NDT, NDT is non-destructive testing, which every Atomic Energy Commission has. And what they do is that they identify materials by non-destructive testing. So you do not want to burn, vaporize the material, and you want to determine what the composition is. This is a field application of neutron activation. Now, neutron activation is a field where you fire neutrons and activate something. Now, when a nuclide gets activated by a projectile neutron, then it goes into an excited state. And it can do one of many things. And one of those things is that it can emit a characteristic gamma ray. So if you have a fast neutron hitting something and you carry out an activation analysis, then we call that fast neutron activation analysis, FNAA. If you fire thermal neutrons and try to do the same thing, then that is called thermal neutron activation analysis. Now, the problem on the field is if you're going to inspect a bridge made of concrete, which is 60 years old, and you're going to see if it has cracks, if it has developed cracks in there. So you have to go to that bridge and you have to fire neutrons, and you have to get the scattered distribution, the spectrum. And from that, you can determine the cracks, or you can have a transmission if you see, the good thing about neutrons is that it is a penetrating radiation. So neutrons and gammas are penetrating radiation. They can also go across a solid. Now, when we go to a hospital, we are fired with X-rays, because if there is a fracture in the bone, then an X-ray, which is a lower energy than a gamma ray, so an X-ray can go through our body and take a picture on the other side. And if there's a crack in the bone, if there's a fracture, then you'll see it in the X-ray film. So now thermal neutrons, you don't have a thermal neutron source. So usually you fire a fast neutron. And so this is the study that in a thermal neutron activation problem, what kind of a moderator do you need to slow it down so that you get a good signal for detection? Okay, now this is an explosives detection system. As you know, many countries of the world where there were wars, so the armies used to go and lay mines. Now mines can be very small butterfly mines. They can be of a few 200 grams. They can be big mines to blow up tanks of the enemy when the enemy is advancing. So these mines are usually hidden under the ground. Now, after the war is over and the armies have gone, so many of these mines left behind, for example, in Bosnia, in Iraq, in Afghanistan, there are many mines. And when children go and play over there, so remember when you were a child, you used to go and run and try to catch a butterfly. So just like that, little boys and girls, if they see a red and yellow and pink butterfly, they go running and get excited to catch the butterfly, and that turns out to be a mine left by some army 10 years ago. So it can kill them, it can blow off their feet and hands. So this is it's a humanitarian effort to design small detection systems which are portable, which you can scan an area where a war has taken place, and it would be very nice if you can demine the area so that it is clear for children and for human beings to just live over there, and grow crops over there or do whatever. So here is a study again. This was a PhD study. There's a paper on it by Hamza Khan, myself. Okay, so this is the front view of a briefcase. So you can see that this is like any Samsonite briefcase, and we've got a source over here. So the source, and there's soil. We're walking over some soil, and let's say under the soil there's some explosive which is hidden away. So that I've colored red over here. So if you fire a neutron beam, a fast neutron beam, so it activates the explosive if there's an explosive. If not, then if there's rock or soil, anything. Okay, it activates it, and what you could get gamma rays coming out of it. You could get backscattered, reflected neutrons coming. And then you can have detectors over here. You can have BF3 detectors, okay, boron trifluoride detectors. You can have sodium iodide detectors. You can have BF3 detectors. You can have sodium iodide detectors. Now, BF3 detectors are used to detect thermal neutrons because you have a moderator like wax before that, and you can you can produce charge. Basically, you ionize the gas and you produce electrical charge and detect the neutrons. Now, for the detection of gamma rays, you can have scintillators, sodium iodide plastic scintillators. So in this portable detection system, we've got a source, we've got a polyethylene shield, as we studied in the earlier lectures, that when a neutron collides with a hydrogenous material, then the chances of it thermalizing are very good. So here it thermalizes. There's a reason why we wanted to thermalize. I'll just show you. And basically we detect it. Then you've got your electronics over here. You could have a FPGA, field programmable gate array, and that could be transmitting the signal from the field that you're scanning, maybe to a small remote controlled helicopter. And you have to now work out the scan time necessary. Can you cover 1 square kilometer, and how many minutes would you take to do that? So that's the front schematic of a fixed source explosives detection system based on thermal neutron activation. Now let's look at the same thing from the top. So here we've got 1, 2, 3, 4, 5, 6 little sodium iodide plastic scintillator detectors. And from the top, you can see that this is the shielding. This is the source, the moderator. Why do we need a moderator? How much moderator do we need? How much shielding do we need? Now, all these are the design calculations that you need to do in nuclear engineering. Now, here's a picture that our system is going to be sitting on top over here. We've got glass tubes over here, and we have a BF3 detector over here. Okay, so we've got a moderator source, we've got BF3 tubes, and the explosive sitting in the ground. So these are the detectors. So let's see how we would analyze this. So we've looked at nuclear assemblies, we've looked at a nuclear reactor, we've looked at the shielding. Now this is another nuclear application of for non-destructive testing. This is another picture of it with a little bit more detail shown on how you're going to place your source and what are the dimensions of the source casing, the top view and the side view. Now, these are the reactions. Okay, so let me show you the reactions and the cross sections. So again, before you do a simulation, you've got to understand the problem. So let's try to understand the problem over here. The problem is that an explosive like TNT is made up of 4 things: carbon, nitrogen, oxygen, and hydrogen. So I'm going to be interested in these 4. Of course, these 4 things are in wood also, and they're in many plastics also. So and they're in drugs also. So how would you differentiate between wood if somebody is taking a plastic plate in their suitcase? Second person is carrying drugs in the suitcase. Third person is carrying explosives in the suitcase. Now you've got a scanner over there, and the scanner goes, and when your suitcase goes on the belt in the airport, then it's scanned, and they want to know from the security point of view that what is inside your baggage. So this is very useful at an airport, at a shipping port, at the entrance of a city. You can have all the cars that are entering the city, they go through a detection port. So now if you fire neutrons, so these 3 reactions are if you fire fast neutrons, what happens? And these 2 are if you fire thermal neutrons, then what happens? Now, so if you fire a 14 MeV neutron on carbon, then it produces a gamma of 4.4 MeV. If you fire on nitrogen, it gives you this. If you fire on oxygen, it gives you this. If you fire a thermal neutron on hydrogen, it gives you a characteristic gamma ray of 2.2 MeV. If you fire on nitrogen, it gives you a characteristic of 10.8 MeV. Now, apart from knowing these nuclear reactions, it is also important to know how many of these reactions will take place. So for that, you need to go and see the cross section, uh, which I plotted over here. I've taken this from KAERI, the Korean Atomic Energy Research Institute website, where they allow you to access cross sections, to plot them, and to define the energy windows, the y-axis, to color it differently. And then I labeled this, I transferred this into MS Paint, and then I labeled. So you can see that the red one is oxygen, so it begins over here and comes out over here. The blue one is natural carbon, the purple one is hydrogen, and that's nitrogen. Now for nitrogen, you begin to see a few resonances over here for oxygen and nitrogen. The important point is that this is a log scale. And you can see that most of the reactions are going to take place at lower energies. Some, of course, over here. So yes, the reaction rate goes up after about 4 MeV and goes up at thermal. So that is why we would prefer thermal neutron activation over here. So let's carry out a study, and you can see that the most you would get is from nitrogen, second most from hydrogen, while from carbon and oxygen 16, from oxygen 16 and carbon 12, hydrogen 1 and nitrogen 14, you'll see the most from here, second most from here, third and fourth, but these are log scales. So you will receive minimal signals from over here. But in this Monte Carlo simulation, what do we need to do? We need to model our source, we need to model our detector, we need to model the soil, and we need to look at how many grams or kilograms of explosive are concealed, how many centimeters deep within the ground can we detect the signal, can we, first of all, can we detect it? Second of all, that having detected it, can we get the chemical formula of the thing that is hidden? Because we want the chemical formula, we want the ratio of the atoms of nitrogen to hydrogen. And then in our FPGA, we could have a lookup table. You could match your results with the database that you've got, and immediately you can say that this is TNT, this is RDX, it's nothing. You know, you can immediately identify within seconds what it is. So here is our tallies, which I showed you, which we're going to do now. So let's define the tally number 24, the multiplier, tally multiplier 24. So I'm going to find the flux and see how many variables there are. Now this is the phase space, 3 and 2, 5 and 1, 6 variables. I've integrated over time, it's a steady state problem. So when we started this series of lectures, I told you that there are 7 variables. But now we've got 3 and 1, 4 and 2, 6 variables. So 6 variables, can you imagine doing this with anything else other than Monte Carlo simulation? So we are going to get an excellent spectrum of flux over here. We are going to multiply it by the microscopic N gamma cross section for hydrogen. Then for nitrogen, we are going to multiply by the number density, and we're going to get the number of gammas which are coming from hydrogen and the number of gammas which are coming from nitrogen, and then we will see the spectrum and do our analysis. Now, because you saw that the cross sections are favorable for thermal, so this is a little lab experiment that you should do, simulate, that put a source, and here's the blue one is your specimen of explosive. And what I told my student, my PhD student to do was take some layers in between and just carry out simulations to see which moderator and how much of it, for example, is graphite good, is water good, is wax good, is polyethylene good, what is a good moderator and how much of it do you need, what will be the weight of the moderator, so that you maximize the N gamma reactions here, because outside over here are going to be your detectors. And you don't have an infinite number of detectors, so you're not going to be able to measure 100% of the signal. Okay, so what do we want at the end of the day? We want the pulse height tally, because this is the connection between people like us and the experimentalist who's sitting in a lab and he or she is going to see something like this, that they've got windows of energy and they're counting the peaks in each bin. So this is my nitrogen peak, 10.8. This is my hydrogen peak. So what I have to do in a simulation is to see how many number counts do I get from hydrogen, how many do I get from nitrogen. Then there are other factors which need to be considered, like the detector efficiency, the solid angle, and so on. So it's a big study, but what you need is the F8 tally over here, which Monte Carlo does have. So I'm going to put that in the input file that I'm going to show you. So this is the input file. That now you see the number. So this is block 1 is from here to here. Sorry, there should be a space over here. So just to show you, I told the word file to remove the space. But this is block 1 coming from 1 to 5. These are the 5 cells, and the surfaces are the second block, which are from 1 to 40. I forgot to tell you, in the last input also I had stars over here. Whenever you put a star on a surface, that means it's a reflecting surface. Okay, so this is a kind of reflecting surface, so any neutron going out of there comes back. The source. I am using a CF252 source. So I use a standard built-in probability. The source probability distribution is called -21. Sorry, the source probability, the energy is distribution 2. So it's SP2, which is a -3 source. And these are the A and B parameters. If you go back in the lectures, you'll see that these are the parameters of a fission spectrum of CF252. Now, okay, so this is the definition of the source. It's along the y-axis, and I'm going to sample the radius of the source from distribution 1. It's a neutron source. It has an energy distribution 2, which I told you about. It is traveling in the y direction, okay, and it's at 90 degrees to the x and z. The distribution 1 for radius is going between 0 and 0.05 centimeters, and this is a distribution, parabolic distribution profile, I think. Please go and check it. So you can distribute things linearly. You can define a PDF, CDF, a histogram, or a parabolic distribution. And I think I put a parabolic. Now this is a thing that you forget after many years, so I should have put a dollar sign over here. Okay, so this is a neutron only problem, so it's a mode neutron. I've got 1 neutron importance for neutron in cell 1. In cell 2, 3, and 4, again, I'm repeating this 1 3 times. So I've got 1 and 3, 4, and the outside world is 0. So I've got 5 cells. I should be having 5 cells. So I've got 1, 2, 3, 4, 5. So this is the outside world. You see, I should have all comment cards over here. So you should do that. And sometimes when you have a lot of experience, you say, oh, I know what all this is, but we're all human and we forget after a number of years what it was. Okay, so now let's define the materials. Water is material 1, H2O. What is this 2, 3? Okay, so that's helium 3. And why did I put helium? I don't think I'm using it here because some detectors are helium detectors. So maybe I wanted at that time to do a study that instead of BF3, I wanted to look at a helium detector. Okay, now let's define wax, B-paraffin, borated paraffin wax, polyethylene. So let's look at 3 possible moderators. Now wax has a density of 0.930 grams per cubic centimeter. This is the composition. A very nice place to get compositions is the Pacific PNNL, Pacific Northwest Nuclear Labs. They've got, it's freely accessible. I use my number densities from there. So from PNNL, you can get your, I think they're called radiation cross-section, cross-section data or radiation compendium of radiation shielding, something like that. Okay, so I've defined material 5, 6, and 7 as the 3 moderators which I'm going to consider. We've got BF3 gas. Now, BF3 gas in this simulation is 96% enriched in boron 510 because B511 doesn't have a good cross section for N alpha. Okay. Now, the BF3 detectors, you can study about detectors, they work on the BN alpha reaction. So it's a neutron capture in the boron trifluoride gas. Because I'd seen these things in the lab where I worked before, so I know that it's a BN alpha reaction is going to take place. So this is the B510, this is the B511 atomic density, this is the fluorine. So you can study what enrichment you need, but if you have lower enrichment than this, it just spoils your signal. I took an energy, 2 groups as before, and I took the tally, F4, the flux tally in regions 1, 2, 3, 4. For the N alpha reaction in cell 4, this is a tube. So I multiplied by the BF3, by the boron density, I made material 11, you can see is boron, and 107 is the microscopic cross section for N alpha reaction. So then I did this again for B10 and B11 separately. I ran this simulation for 4,000 particles, which is very small when you're doing a paper or your PhD thesis. I remember my student took 400,000. So carry out a big proper simulation. Now these are the results which I'm going to show you. This is one tube. So yellow is the gas and the blue is the moderator, and purple is some other medium in which the source is placed and fired. Okay, that's surface 1, surface 2, and try to make the input files yourself. If you want me to send you, you can email me and I'll send you. Okay, now in this study, you can see that we varied the moderator thickness between the source and the BF3 tube, and we did a count on the N alpha reaction. So can you see that when it's going up from 1 to 2 to 4 centimeters, it goes up, but then it starts going down. So somewhere between 4 and 6 centimeters thick, I think this is wax, we've got the optimal. So what we did over here was that we looked at this region 3 to 5.5 a little bit more carefully, and you see that somewhere over here is the maximum. So why is it so important to get the optimal moderator thickness? Because you're going to take something out in the field and you want the best possible optimized design. So when you plot these numbers over here, you see that as a function of the thickness of moderator delta R in centimeters, so the BN alpha reaction rate goes up, 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 stabilizes, saturates, and then starts coming down. So here's the optimal thickness, about 4 centimeters. Now this depends on the material of the moderator. So what we did was that here you see energy and flux plotted. Now here I think we have more than 100 evaluations of the flux. So made about 100 or more energy bins, big input file. So we saw what the spectrum looks like for 2 centimeters, see? Then for 4 centimeter also is good. But if you exceed 4 centimeters, then look at the spectrum. It reduces in this end as well as in that end. And the BN alpha cross section, just to show you on the same figure, in 10, isotope 5B10, you can see that it goes up on the log scale. So yes, we do want thermal neutrons. So this shows you that there's an optimum close to about 4 centimeters. So this is the study that you need to carry. This is the signal that we get from our portable detector. And now this signal has got so many pulses. And can you see that this is 2.22 MeV? So this is the nice hydrogen peak. We've got about, so this is 10,000, 20,000, 30,000. Sorry, this is 10 to the minus 4 photons per centimeter square per second. So you've got to multiply this by the californium source strength, which is about 10 to the 7. So when you multiply this by 10 to the 7 that we took, or 10 to the 8, so you get about 20,000 counts over here. So you get about 20,000 counts, and then of course you've got to do a study that what is the soil in your area. Is it calcium carbonate limestone? Is it sand? What is it? And so this is the nitrogen peak that you see, the 10.8 MeV. These are the other peaks, and you've got to see tables of the various peaks that you get. So from the relative intensity of this to this, you identify whether you have an explosive or not, and then you work out the chemical formula of this unknown sample. And from that, we did all the simulations, and we found that yes, you can detect explosives, and these things are being developed. And in the next few years, you'll find these kind of explosives which are freely available and used at airports and dry ports, and when cars are entering cities, leaving, so for the safety and security systems, and for humanitarian demining, which is so important. Okay, so in these lectures, you learned applications of Monte Carlo simulations. These are very, very strongly recommended to nuclear engineers. And you see, the theory that you study in your classroom is for a purpose. And that purpose is to design nuclear systems. Because before you go and do anything practical, you must simulate. Because nuclear is a field where safety, just like industry, just like any engineering thing, safety is the most important thing. After safety comes economics and functionality. So nothing is more important than safety. And if you read about industrial accidents, you'll see, read about Chernobyl, read about the Bhopal Union Carbide accident. And there are so many industrial bad things that happen where people lose their lives. So as engineers, our foremost consideration is safety. So in this course, NE402, my objective as somebody who's worked 35 years, out of which I had a small 1 year. My first experience was in Exxon Chemicals at the fertilizer plant, which operates at 3000 PSI. So, chemical industrial safety is so important. Nuclear safety, so important. So that is why in these 3 or 4 lectures, I took you through practical applications, which often in undergraduate studies, we are not taught. And I certainly wasn't. And so I learned, because in those days, we didn't have so many computer codes, we didn't have systems, we didn't have the internet, we didn't have laptops. So we were a bit slow, we had to read books, and our education was very different. So your education, especially in the lectures, and these lectures which I'm uploading on YouTube, I think that I'm giving all that I have learned, and really this is wealth of tying up your theory with applications. And if you have seen these things with your eyes and you've touched them, then you understand which equation applies over here. And believe me, when you're in a work environment, you don't have time to read books. You have time to do things, because industry demands you to do things. And you have to be so fast that it's your reflexes which are important. Okay, so I hope you've learned Godiva, you've learned Clark's criticality experiment, you've learned reflected spherical reactor, cylindrical homogeneous reactor, radiation shield, explosive detection system. I'm now confident that you can go and tackle any big problem, and you will see that you understand things, you understand the physics of it, you understand the mathematics of it, you understand the science of it, you understand the engineering of it, and you understand what good is it to society. Okay, so that's the end of this lecture.